Okay, 7O part C, and centrifugal. I almost said it, and that word, I'll tell you about that word, it doesn't exist. Centripetal force. Do the worksheet, do all of it, okay? Now, for this worksheet, you're going to go back and look at the worksheet from last lesson, and then you're going to kind of like write down describing it, what's going on. You're going to write some little sentence phrases you're going to fill in. Sorry about this. So you got to look at the old worksheet, and I didn't assign number 4 last time, but go on and try work number 4. But when you do the new worksheet, number 4, try to do it. Number 4 also. Try to do the entire new worksheet. But for C and D, it might get a little tough, and I'm going to go back over that in the next lesson. Okay, so the way this works, I still have my little piece that I made the other day in class to spin this around. The way this works is, we talked about centripetal, well, we talked about uniform circular motion and something called centripetal acceleration. Okay, well, look, I have a little ball. This is a lot better now to see this ball moving around. Okay, so that ball is moving around in this circle. If I come back, you can see a little red ball going. It actually works out pretty good. That's a lot better than the other. Whether it's that way or whether it's this way. Oh my. Okay, like that. I don't want to hit myself. Okay, I better be careful. Well, anyway, in order for something to accelerate, and we know it's accelerating because it's constantly moving in a circle. Remember, Newton says that this ball, little red ball, it should move in a straight line, and at the same speed and the same speed, same direction until a force acts on it. Okay, well, it's not. It's curving. So the only way it can curve is it would have to have a force acting on it, and so there's a force that causes that. All right, so I know the last lesson I did 7A and B kind of together, 7.0 A and B. So it's called centripetal force. Now, it's interesting because there's a word, and I'll tell you now, right now, centrifugal force. And you know what? It's interesting, and I'll tell you the meaning of that. But centrifugal means a force that would be like from pushing outward on you. And it doesn't exist. It's not real. It's an illusion when you're being spun around on a ride, like if you're on a ride at like Magic Mountain or somewhere. You know, you go around on that one where you, or a lot of fairs have these, not just there, but like, I don't even know if they have it at Magic Mountain, but I think they do. But it's like you stand in this like cylinder kind of thing, and everybody stands, around the walls of it, and you spin around real fast, and then the floor drops down, and you're stuck to the wall. Okay, but what's amazing is, it seems, in your mind, it seems that there's a force pushing outward on you, pushing outward and pushing you against the wall. But actually, there's not. What's really happening is, the wall is pushing on you. And it is really strange. You feel like you're being pushed against the wall, but it's really pushing on you. Because it's kind of like I told you the other day, if I could, I don't know how you could do it that way, but if you could spin someone around, like when you spin someone around, like in a circle this way, they hold your hand, a little child, you're going around in a circle, you do that outside on the grass or something. When the little child holding it, it feels like there's a force pulling them away. Like I told you, it feels almost like if I let go of your hand, you're just going to fly away out there. Well, that's an illusion, believe it or not. And I told you that what will really happen if you let go of their hand, they're going to fly that way. So you're keeping them in a circle. The force is actually coming this way. The force always acts to the center of the circle. Isn't that strange? So it's called centripetal force, just like centripetal acceleration means toward the center. That means out from the center, and it is a word in English. You can look it up, but in physics, it actually is not true. It's an illusion force. It doesn't exist. But you feel like it, but it doesn't. It's really weird. All right. By the way, in this lesson I'm doing, I'm not going to do a whole lot of. Well, I might do a little bit of math in here. Yeah, I guess I am going to do some math. But your math, your homework is going to be pretty easy. this time. Then the next lesson they'll get a little bit more involved because you're going to look at the old problem and you're going to analyze what's going on in that. Okay, so first centrifugal force. I talked about that. All right, the next thing. Oh, I got my notes out of order. I didn't staple it yet. What did I do? Oh, here it is. Okay. That's the back. Page 2. Okay. I'll just talk about centrifugal and all that force. Now, it says this. Oh, you've also heard of a centrifuge before. You might have heard of centrifuge when you spend. It's actually in chemistry. Actually, I have some chemistry here. Look, I have some chemica. Now, what a centrifuge does, it looks like blood, doesn't it? That's more. I can talk about that. Take AP chemistry next year. But anyway, there can be some solid material at the bottom, and so it's not blood, but it has a chemical iron in it and something else that makes it look a lot like blood. If I spin this thing around in a centrifuge, it spins it around, and all the solid dust comes to the bottom and it collects down here. That's what a centrifuge does. Now, if you didn't use a centrifuge, you just wait like a few days, and it will, or not even that long, maybe a day or so, and it will slowly all filter down to the bottom. But a centrifuge will do it like in 5 minutes. So a centrifuge, it spins around. It's like I don't know why I was talking about that, but go because there's a question about it. So I'll draw a little. Pretend you have a tube here. You have a tube here. You always have to have some opposite each other, or it'll be out of balance. 2 will work, or you can do 4. Okay, 1 there, 1 there. And it spins around. And so what happens is any particles that are in there, they get moved all the way to here. They get moved to the bottom. Well, anyway, what's interesting is the question said, it's right there under centrifugal force. That's not a big deal. When a mixture of water and powder is in a test tube separated by a centrifuge, what is the direction of the force acting on the material? The force is actually pulling it toward the center. And isn't that weird? Because again, if I let go, it will fly out that way. It would. But you're holding it in place. And what you're doing is, instead of letting it fly out that way, it comes close. It has to come back into the circle. It stays in a circle all the way around. That might be a little tougher to get that. You don't even have to worry about this stuff here. I better just jump to a problem and show you. Now, I'm just going to do 1 or 2 problems, and then next time let me see. Yeah, I'll do A and B. And, all right, this will explain what the lesson is going to be like. Anyway, what you're going to have to do. What do I need to do? Okay, A. It says this, and it's so simple. A girl holds a 13-gram rubber stopper attached to a string. Stopper is swung in a horizontal circle, making one revolution in 1.18 seconds. Now, even though this is not a rubber stopper, it's the same deal. So she's doing this, okay? I don't want to get hit by that thing. I'm not kind of trusting it. So the thing that they're telling you is the little stopper, which is the ball here, we'll say, is 13 grams. So the mass, 13 grams. Now, I'll do this because I know right off. In physics, it has to always change it into kilogram. So you divide by 1,000. But if you want to do it this way, gram, kilogram, 1,000. 13 divided by 1,000 will be 123.013 kg. If you want to do it that way, the mass is 0.013 kg. All right, what else did they tell you? It's attached to a 0.93 meter string. Now, that they're telling you, assuming that that's the radius. Now, that's not 0.93 meters from my finger to there, but we'll pretend it is. 0.93 is the radius. So, you might draw a little diagram. Here's a little ball, whatever. 0.93 meters. That's that distance from there to there. Okay? So the radius is 0.93 meter. Then it says it makes 1 revolution. So we're going around and around and around in 1.18 seconds. So actually, to be fair, this thing is like almost a meter, like a yard long. And she's swinging it around like this. 1.18, that seems to me like too long of amount of time, but we'll use it anyway. So the time. All right. Oh, I put seconds. Sorry about that. Well, there's a special name for that. Remember, it's not the time, but it's the capital T, the period. The period. Let me think. Why would I need to do that? Oh, I know. Sometimes we'll say something like, in 1 minute, it'll make 100 revolutions in 1 minute. And you think, well, how many would it make in 1 second? So you get to divide that by 60. 100 divided by 60. So anyway, I'll get to that part. All right, we don't have to worry about that here, but read the question carefully. Sometimes they give you the time it takes to go in a circle, or sometimes it's the time. Sometimes they give you the total time. Forget that. We're only going to see the period right now. Okay, so the first question, number 1, says, find the tension in the string. Tension? Wait a minute. We did that a while back in an older chapter. Tension is the force in the string. And look at this. So we have all the equations from last time, and I don't have them written down here, but centripetal acceleration is v squared over r, or it's 4 pi squared r over the period. The velocity is 2 pi r over period. And here's a new equation. Remember F equals ma? This is all the math. The only thing new today is this. Centripetal force is mass times centripetal acceleration. So look how easy this will be. You're going to find out that it's not going to be very hard when you do your work. Most of your work will be filling in the blanks, thinking about the question, and then doing a quick math problem. But here we go. Well, I guess you are going to do number 4. That's the only thing that you didn't do before. And if you have a problem with that, don't worry. Just try it at least, because there's a little bit there that I'll have to explain next time. Okay, here we go. So let's first of all, we want to know, what is the force? The force is the tension. Tension is the force. All right, tension is the force. This is a centripetal force in the rope. That's just keeping it in place. So first, let's find the acceleration. Now, it looks like we don't have the velocity, so we'll have to use this equation. Velocity is, well, you can use 2 pi r over t, but they didn't actually ask. They didn't ask for the velocity, so we can just jump to this one. So this is why it's good to use that equation. All right, this is a good opportunity to use this equation, because you don't have to. They didn't ask you to find all the other part. So the acceleration is 4 pi squared r. 4 pi is 3.14. We're going to square it though, and the radius is 0.93 meters, divided by the period, 1.18 seconds. Oh, wait a minute. Is it? Oh boy, I almost forgot my own equation. Is it 4 pi? Yeah, it's t squared. Yeah, I'm glad. Hey, I remembered before I just did it. I remembered that it needed to be squared. Okay, 1.18 has to be squared on the bottom. In the equation, I forgot to write it there and there, but then I looked on my paper real quick and I said, wait a minute. Yeah, I knew that there was something weird there. Okay, so, oh boy, 3.14 squared times 4 times 0.93 divided by 1.18. 1.18 again, 1.18 squared. So 26.3 is acceleration. Centripetal acceleration is 26.3 meter per second squared. Let me double check it again. 3.14 squared times 4 times 0.93 divided by 26.3. Got it. Okay, that was I'm still doing number 1. I'm not finished yet. What is the tension in the rope? Well, the tension will equal the centripetal force. Centripetal force is MAC. In fact, I could just do the math. I could just do it over here. Why not? I mean, whatever, underneath that one. The mass is 0.013 kg. And the acceleration is 26.3 meter per second squared. And look how easy that is. That's the whole thing. 0.34 newtons. Very small, but it's a small piece. It's like that little ball I have. That's a small force to keep it in a circle, to keep it moving around. All right. So then look at question number 2, and it says this: in this situation, the force or the tension is being applied to blank, and the agent applying the force is blank. So all right, here it says, in the situation, the force is being applied to the rubber stopper. Okay, and the agent applying the force is the rope or the string. The string is pulling it this way. As he's spinning around, it's always centripetal toward the center. You're always pulling it toward the center. Now, since it's moving that way, but it just stays in a circle, and at every moment you're always keeping it in toward the center. Keep pulling it toward the center, keeps it in the circle. Okay. All right. Then there's one more question, and it says, this one. Okay, I'll have to check it on as far as this is the one that involved the friction too, but I don't know if I'm going to have that here. All right. So this one, it says an 80 kilogram runner, number 2. So the mass is 80. I think this is like one of the problems on your work that number 4 I told you about. 80 kilogram runner moving at a speed of 8.8 meters per second. The velocity is 8.8. Rounds a bend with a radius of 25 meters. So what we're doing, even though they're probably on a track like that, all we care about is the end part of the track. So like on the end part of the track, let's say you go around a circle, you're pretending that's like, what's the radius of that circle right there? That's the radius, and he runs around that. And during that period, we can apply uniform circular motion. So first of all, what is the acceleration of the runner? All right, this is easy on this one because they gave us the velocity. So the acceleration is v squared over r, 8.8 meter per second squared divided by 25 meter. Okay. It's 3.10 meter per second squared. Double checking the math there. Okay, number 2 says, what force is being applied to the runner as he rounds a bend? Oh, that's also easy. F equals ma. But Fc is mac, M-A-C. So he is 80 kilograms. Oh, I forgot that I can also stand here. Haha. I was doing, is it this class I did the video, or I don't know. I never realized that till I've been making these videos a long time. I didn't realize I could stand over here. And then I can be like out of the way. Well, whatever. I'm going to end up, I say that and I'm probably like, you're blocking it. Okay, 3.10 meter per second squared. All right, 80 times 3.10. 248. Is that right? I guess it is right. 80 times 3.1. Yeah, 248 newtons. That's the centripetal force on him. Now, in this situation, this is an important one. The force is being applied to blank, and the agent applying the force is blank. So, as someone's in track, and he or she is running around the bend there, the force is being applied to the runner's shoes, okay? And it's being applied by you could say the friction between the track and the shoes. So the track would be applying force to the shoes. That's what's going on. And you know that because if you try to run in oil, like a garage was oily or whatever, you try to do a circle, you're not going to be able to, you're just going to slide straight forward. You're not going to get any traction. Traction is the word from the track. The traction, when we say the word traction, what it really means is it's that's allowing the ground to put force on your shoes. Okay, because of friction, because there's friction between your shoe and the ground, you won't slide. It'll keep you. You're not overcoming static friction. Kind of a weird thing. I don't want to confuse you about that, but anyway, the force is applied by the track on the runner's shoes. And then number 4 says, this is the part that I was saying might be hard. I didn't know it was in today's lesson. What is the minimum coefficient of static friction necessary to keep the runner's shoes from sliding on the ground? Okay, this is a little bit crazier, but I'll show you. It's not too hard. The friction force has to equal, it says minimum force. It has to at least equal the centripetal force, 248. So the centripetal force equals the friction force. So remember, friction force is mu K times the normal force, which means mu K. In this case, the person's running. We're not going to worry about if they're angled over a little bit. We're just going to say it's going to be their weight. Their mass, their weight, we'll say that their normal force equals the weight, okay? And it should be in this because they're a flat horizontal surface. So it'll be mg, because weight is equal to mg. So I'm putting all this into one problem. The friction force is mu k times the normal force. The normal force is the weight. Okay, I can put F weight there, mg. So if the friction force is 248, we don't know the friction constant, but we know the mass of the person, the runner, is 80. And we know G, gram, is 9.81 gravity. So there it is, 248 divided by 80, and then divided by 9.81 gives you 0.316 is the coefficient of friction. I think it will come back on the next video too as well. I didn't know that was in here, but hey, if you can do that, that's great. That's probably the most challenging thing you'll see. But this worksheet's going to be kind of short, except for doing number 4. It's just yesterday you did 3 problems. You're just going to do 1 problem, number 4. But then you're going to go over to the new paper and you're just going to, for all the problems, you're just going to say, okay, force is MA. Or remember, when we say tension, it's also the tension force is also MA. So that's all you're doing there. All right, I'll see you guys later on.